Hey everyone, it's Justin again. We learned a little more about vertical asymptotes when we talked about discontinuities. In today's lesson, we'll take a closer look at horizontal asymptotes. By the end of this lesson, you should be able to find horizontal asymptotes from the equation of a rational function. First, we'll review horizontal asymptotes in graphs, and then we'll learn how to find a horizontal asymptote from a function's equation. Then, we'll practice with a couple examples. Before we dive into the lesson, there's a common misconception about horizontal asymptotes that we want to take some time to mention. Take a look at this graph. As the polynomials in rational functions become more complex, the graphs will get a little more complex as well. There's something interesting happening here. It looks like this would be a horizontal asymptote, but it also looks like the function passes through the dashed line. Does that mean it's not an asymptote? Actually, it's perfectly okay for a graph to pass through its asymptote. If this feels weird, it might be because you've heard an asymptote described as a line where the graph gets closer and closer but never actually reaches. But a horizontal asymptote is not defined by the fact that a function can never reach that value. Instead, what makes it an asymptote is that the function gets closer and closer to that value as you go infinitely far left or right. It's okay if the function crosses the line somewhere in the middle. The asymptote only tells us about what the function is doing off into the distance. On the other hand, a function will never cross its vertical asymptote, since the function doesn't exist at that x value. Remember, a vertical asymptote is a type of discontinuity. Okay, now we can get started on some deeper analysis of horizontal asymptotes. Let's take a look back at the graph of good old 1 over x. Its horizontal asymptote was at the line y equals 0. Even when we reflected or dilated this function, the horizontal asymptote didn't change. And this wasn't the only function with a horizontal asymptote at y equals 0. The same asymptote is found in the function 1 over x squared. In fact, there are many rational functions with horizontal asymptotes at y equals 0. Take a look at this weird looking graph. It may look different in some ways, but it's still a rational function, and it still has a horizontal asymptote in the same place. Not every rational function has the same asymptote, but many of them do. And there's actually a way to check just by looking at the equation, whether or not there is a horizontal asymptote at y equals 0. For any rational function where the degree of the numerator is lower than the degree of the denominator, the horizontal asymptote will be at the line y equals 0. Remember that we use the word degree to refer to the highest exponent found in a polynomial. For example, the degree of the first polynomial here is 3, and the degree of the second polynomial is 5. If these were the numerator and denominator of a rational function, then by this rule, the function would have a horizontal asymptote at y equals 0. Now, you may recall that for 1 over x, there was a way to move the horizontal asymptote. Take a look at these graphs, which are vertical translations of the parent function 1 over x. Do you remember how to write the equations for these graphs? There's a vertical shift in both graphs here, which is done by adding or subtracting a number from the function as a whole. In the first graph, the shift is down 1. So the equation would be 1 over x minus 1. In the second graph, the shift is up 2. So the equation would be 1 over x plus 2. In both of these functions, the degree of the numerator is 0 because there aren't any x's in the numerators. And the degree of the denominator is, of course, 1. But these functions have horizontal asymptotes in different places. Doesn't this break our rule that if the degree of the numerator is lower than the degree of the denominator, then the function should have a horizontal asymptote at 0? Well, remember, our rule is for rational functions. These graphs here are translations of a rational function, but the equation of a true rational function is only a polynomial over another polynomial. It all has to be one fraction. These equations don't fit that description, so the rule doesn't apply. But we could actually make common denominators and turn these equations into a single fraction. Then they would be rational functions. So let's see what happens if we do that. Here are the two equations from those graphs. We can create a common denominator of x to turn both of these functions into one fraction. In the f of x equation, -1 can be written as minus x over x. And in the g of x equation, +2 can be written as plus 2x over x. Then we can combine each into one fraction like this. Now, these are true rational functions. Notice how in our new equations, we end up with the same degree in the numerators as in the denominators. It's not a coincidence. It's actually the reason why these graphs have different asymptotes. This leads us to a new rule we can use. For any rational function where the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote will be at the line y equals a over b, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. That's a lot of words, but in practice, it's just one quick step. Here's an example. If the degrees of the numerator and denominator are equal, then take the leading coefficients, which are the numbers attached to the highest power of x, and divide them. This rational function would have a horizontal asymptote at the line y equals 5. Now we have rules for what happens if the degree of the numerator is less than the degree of the denominator, and if the degrees are equal. We should also mention what happens when the degree of the numerator is greater than the degree of the denominator. When this happens, that means there's no horizontal asymptote. For example, this function would not have a horizontal asymptote because the numerator has a higher degree. And that's all there is to say about this last rule. So let's take a look at all three of these rules again before we move on to some examples. For any rational function, the following is true. If the degree of the numerator is lower than the degree of the denominator, then the function has a horizontal asymptote at y equals 0. If the degrees are equal, then the function has a horizontal asymptote at y equals the ratio of the leading coefficients. And finally, if the degree of the numerator is greater than the degree of the denominator, then the function has no horizontal asymptote. Now that we have this list of cases, let's tackle some examples. Here's example number 1. Find the horizontal asymptotes of these functions. This problem has two parts, so let's just focus on part A for now. We have to look at the degree of the numerator and the degree of the denominator. The largest degree we see in the numerator is 3, so that's the degree of the numerator. Then in the denominator, the highest degree we see is 4. It looks like we have case 1 here. The degree of the numerator is lower than the degree of the denominator, so our horizontal asymptote is y equals 0. Let's move on to part B. Let's find the biggest degree in the numerator. What's the highest degree in the numerator? Here it is. It's 4. The exponents here weren't in order from largest to smallest, but that didn't trick us. And in the denominator, the highest exponent is also 4. Okay, you've got this. Take it from here. Find that horizontal asymptote. Did you refer back to our list of options? This time, case 2 is going to help us out. Since the degrees in the numerator and denominator are both 4, we can look at the coefficients in front of them. The coefficients in front of those highest terms are 7 and 2. So we divide 7 by 2. We can write our horizontal asymptote as y equals 7 over 2, or y equals 3.5. Now, we have both of our answers for this example. We'll do one more example. Which of the following could be the equation of the function depicted? Let's focus on the graph first. Do you see a horizontal asymptote? I sure don't. This definitely approaches some line, but it's not a horizontal line. It looks like we're working with case 3 here. There is no horizontal asymptote. So now we know that we need an equation where the degree of the numerator is greater than the degree of the denominator. So let's go back to our options and look at those degrees. Go ahead and find the highest degree in each numerator and denominator and see if you can answer the question. Pause the video and try it. All right, let's see. Here are the highest exponents in each numerator and denominator. The function with a higher degree in the numerator is the first one. The numerator is degree 4 and the denominator is degree 3. Therefore, this is our answer. In this video, we learned how to analyze a rational function to tell the equation of its horizontal asymptote, or to determine if it doesn't have one. But like you saw in the last example, some functions can actually have slanted asymptotes. And that is the subject of our next video. See you then. Hey, hey.